Today, excuse me. Today is 25th March. I'm reading from Using SQLite by John A. Krebich. I'm continuing my reading of chapter 4 today, and today's section is update. The update command is used to assign new values to one or more columns of existing rows in a table. The command can update more than one row, but all of the rows must be part of the same table. The basic syntax is update table name, set column name to a new value, where, then the expression. The command requires the table name followed by a list of column name value pairs that should be assigned. Which rows be updated is determined by a conditional expression that is tested against each row of the table. The most common usage pattern uses the expression to check for equality on some unique terms, such as unique column, such as the primary key column. If no where condition is given, the update command will attempt to update the designated columns in every row of a table. It is not considered an error if the where expression evaluates to false for every row in the table, resulting in no actual updates. Here is a more specific example. Update the price and stock of part ID 454. Update parts set price to 4.25, stock 75, where part ID is 454. This example assumes that the table parts has at least three columns, price, stock, and part ID. The database will find each row with a part ID of 454. In this case, it can be assumed that part ID is a primary key column, so only one row will be updated. The price and stock columns of that row are then assigned new values. The full syntax for update can be found at update in Appendix C. Delete. As you might guess, the delete command is used to delete or remove one or more rows from a single table. The rows are completely deleted from the table. The command requires only a table name and a conditional expression to pick out rows. The wire expression is used to select specific rows to delete, just as it is used in the update command. If no where condition is given, the delete command will attempt to delete every row of a table. As with update, it is not considered an error if the where expression evaluates to false for every row in the table, resulting in no actual deletions. Some specific examples, like delete the row with row ID 385, delete from parts where part ID is 385, delete all rows with a row ID greater than or equal to 43 and less than or equal to 246. These examples assume that we have a table named parts that contains at least one unique column named part ID. As noted, if no where clause is given, the delete command will attempt to delete every row in a table. SQLite optimizes this specific case, truncating the full table rather than processing each individual row. Truncating the table is much faster than deleting each individual row. But truncation bypasses the individual row processing. If you wish to process each row as it is deleted, provide a where clause that always evaluates to true. Delete from parts where 1, delete all rows, force per row processing. The existence of the where clause will prevent the truncation, allowing each row to be processed in turn. The query command. The final DML command to cover is the select command. Select is used to extract and return values from the database. Almost any time you want to extract or return some kind of value, you will need to use the select command. Generally, the return values are derived from the contents of the database, but select can also be used to return the value of simple expressions. This is a great way to test out expressions. For example, SQLite, select 1 plus 1, 5 star 32, ABC or DEF, 1 is greater than 2. So each of them will evaluate to the following. 1 plus 1 will give 2. 5 multiplied by 32 will give 160. ABC concatenated DEF will give ABC DEF. And 1 is greater than 2 will give 0. Select is a read-only command and will not modify the database unless the select is embedded in a different command, such as a create table as select or an insert into select. Without question, select is the most complex SQL command both in terms of syntax as well as function. The select syntax tries to represent a generic framework that is capable of expressing a great many different types of queries. Where it is somewhat successful at this, there are areas where select has traded away simplicity for more flexibility. As a result, select has a large number of optional clauses, each with its own set of options and formats. Understanding how to mix and match these optional clauses to get the results you are looking for can take some time. While the most basic syntax can be shown with a good set of examples, to really wrap your head around select, it is best to understand how it actually works and what it is trying to accomplish. Because select can be so complex and because select is an extremely important command, we will spend the whole next chapter looking very closely at select and each of its clauses. There will be some discussion about what is going on behind the scenes to provide more insight into how to read and write complex queries. For now, we'll just give you a taste that should provide enough information to play around with the other commands in this chapter. The most basic form of select is select output list from output table where row filter. The output list is a list of expressions that should be evaluated and returned for each resulting row. Most commonly, this is simply a list of columns. The output list can also include a wildcard that includes all known columns should be returned. The from clause defines the source of the table data. The next chapter will show how tables can be linked and joined, but for now we'll stick to with querying one table at a time. The where clause is a conditional filtering expression that is applied to each row. It is essentially the same as the where clause in the update and delete commands. Those rows that evaluate to true will be part of the result, while the other rows will be filtered out. Consider the table. Create table ABC ID integer primary key. Insert into table ABC values 10, 10, 10. Insert into table ABC values 11, 15, 20, and another set of values. We can return the whole table like this. We can also just return specific columns like select AC from DBL or specific rows. Select star from DBL where ID is equal to 2. For more specifics, see chapter 5 and select in appendix C. Transaction control language. The transaction control language is used in conjunction with the data manipulation language to control the processing and exposure of changes. Transactions are a fundamental part of how relational databases protect the integrity and reliability of data they hold. Transactions are automatically used on all DDL and DML commands. ACID transactions. A transaction is used to group together a series of low-level changes into a single logical update. A transaction can be anything from updating a single value to a complex multi-step procedure that might end up inserting several rows into a number of different tables. The classic transaction example is a database that holds account numbers and balances. If you want to transfer a balance from one account to another, that is a simple two-step process. Subtract an amount from one account balance and then add the same amount to the other account balance. That process needs to be done as a single logical unit of change, should not be broken apart. Both steps should either succeed completely, resulting in a balance being correctly transferred, or both steps should fail completely, resulting in both accounts being left unchanged. Any other outcome where one step succeeds and the other fails, it's not acceptable. Typically, a transaction is opened or started as individual data manipulation commands are issued. They become part of the transaction. When the legal logical procedures are finished, the transaction can be committed, which applies all of the changes to the permanent database record. If for any reason the commit fails, the transaction is rolled back, removing all traces of the changes. A transaction can be manually rolled back. The standard for reliable, robust transactions is the ACID test. ACID stands for atomic, consistent, isolated, and durable. Any transaction system worth using must possess these qualities. Atomic. A transaction should be atomic in the sense that change cannot be broken down into smaller pieces. When a transaction is committed to the database, the entire transaction must be applied or the entire transaction must not be applied. It should be impossible for only a part of a transaction to be applied. Consistent. A transaction should also keep the database consistent. A typical database has a number of rules and limits that help ensure that the stored data is correct and consistent with the design of the database. Assuming a database starts in a consistent state, applying a transaction must keep the database consistent. This is important because the database is allowed to and often required to become inconsistent while the transaction is open. For example, while transferring funds, there is a moment between the subtraction of from one account and the addition to another account that the total amount of funds represented in the database is altered and may become inconsistent with a recorded total. This is acceptable as long as the transaction as a whole is consistent when it's committed. Isolated. An open transaction must also be isolated from other clients. When a client opens a transaction and starts to issue individual change commands, the results of those commands are visible to the client. Those changes should not, however, be visible to any other system accessing the database, nor should they be integrated into the permanent database record until the entire transaction is committed. Conversely, changes committed by other clients after the transaction was started should not be visible to this transaction. Isolation is required for transactions to be atomic and consistent. If other clients could see half-applied transactions, the transactions could not claim to be atomic in nature, nor would they preserve the consistency of the database as seen by other clients. Durable. Last of all, a transaction must be durable. If the transaction is successfully committed, it must have become a permanent and irreversible part of the database record. Once the success status is returned, it should not matter if the process is killed, the system loses power, or the database file system disappears upon restart. The committed changes should be present in the database. Conversely, if the system loses power before a transaction is committed, then upon restart, changes made within the transaction should not be present. Most people think that the atomic nature of transaction is their most important quality, but all four aspects of must work together to ensure the overall integrity of the database. Durability especially is often overlooked. SQLite tries extremely hard to guarantee that if a transaction is successfully committed, those changes are actually physically written to permanent storage and are there to stay. Compare this to traditional file system operations, where writes might go into an operating system file cache. Updates may sit in the cache anywhere from a few seconds to a few minutes before finally being spooled off to a storage. Even then, it is possible for the data to wait around in device buffers before finally being committed to physical storage. While this type of buffering can increase efficiency, it means a normal operation really has no idea when its data is safely committed to permanent storage. Power failure and disappearing file systems may, may seem like rare occurrences, but that's not really the point. Databases are designed to deal with absolutes, especially when it comes to reliability. Besides, having a file system disappear is not that radical of an idea when you consider the prevalence of flash devices, flash drives, and USB thumb drives. Disappearing media and power failures are even more commonplace when you consider the number of SQLite databases that are found on battery operated handheld devices such as mobile phones and media players. The use of transactions is even more important on mobile phones on devices like this, since it is nearly impossible to run data recovery tools in that type of environment. These types of devices must be extremely robust, and no matter what the user does, including yanking out flash drives at inconvenient times, the system must stay consistent and reliable. Use of a transactional system can provide that kind of reliability. Transactions are not just for writing data. Opening a transaction for an extended read-only operation is sometimes useful if you if you need to gather data with multiple queries. Having the transaction open keeps your view of the database consistent, ensuring that the data doesn't change between queries. That is useful if, for example, you use one query to gather a bunch of record IDs and then issue a series of queries against each ID value. Wrapping all the queries in a transaction guarantee, all of the queries see the same set of data. SQL transactions. Normally, SQLite is in auto commit mode. That means that SQLite will automatically start a transaction for each command, process the command, and assuming no errors were generated, automatically commit the transaction. This process is transparent to the user, but it's important to realize that even individually entered commands are processed within a transaction, even if no TCL commands are used. The auto commit mode can be disabled by explicitly opening a transaction. The begin command is used to start or open a transaction. Once an explicit transaction has been opened, it will remain open until it is committed or rolled back. The keyword transaction is optional. Begin, deferred, immediate, exclusive transaction. The optional keywords deferred, immediate, or exclusive are specific to SQLite and control how the read-write logs are acquired. If only one client is accessing the database at a time, the locking mode is largely irrelevant. When more than one client may be accessing the database, the locking mode defines how to balance peer access with ensured success of the transaction. By default, all transactions, including autocommit transactions, use the deferred mode. Under this mode, none of the database locks are acquired until they are required. This is the most neighborly mode and allows other clients to continue accessing and using the database until the transaction has no other choice but to lock them out. This allows for other clients to continue using the database, but if the locks are not available when the transaction requires them, the transaction will fail and may need to be rolled back and restarted. Begin immediate attempts to require a reserved lock immediately. If it succeeds, it guarantees that the right locks will be available to the transaction when they are needed, but still allows other clients to continue to access the database for read-only operations, but still allows other clients to. The exclusive mode attempts to look out all other clients, including read-only clients, although the immediate and exclusive modes are more restrictive to other clients. The advantage is that they will fail immediately if the required locks are not available, rather than that after you have issued your DDL or DML commands. Once the transaction is open, you can continue to issue other SQL commands, including both DML and DDL commands. You can think of the changes resulting from these commands as proposed changes. The changes are only visible to the local client and have not been fully and permanently applied to the database. If the client process is killed or the server loses power in the middle of an open transaction, the transaction and any proposed changes it has will be lost. But the rest of the database will remain intact and consistent. It is not until the transaction is closed that the proposed changes are committed to the database and are made real. The commit command is used to close out a transaction and commit the changes to the database. You can also use the alias end. As with begin, the transaction keyword is optional. Once a commit has successfully returned, all the proposed changes are fully committed to the database and become visible to other clients. At that point, if the system loses power or the client process is killed, the changes will remain safely in the database. Things don't always go right. However, rather than committing the proposed changes, the transaction can be manually rolled back, effectively canceling the transaction and all of other changes it contains. Rolling back a set of proposed changes is useful if an error is encountered. This might be a database error, such as running out of disk space halfway through inserting a series of related records, or it might be an application logic error, such as trying to assign an invoice to an order that does not exist. In such cases, it usually doesn't make sense to continue with the transaction, nor does it make sense to leave inconsistent data in the database. Pretty much the only choice is to back out and try again. To cancel the transaction and roll back all the proposed changes, you can use the rollback command. Again, the keyword transaction is optional. Rollback will undo and revert all the proposed changes made by the current transaction and then close the transaction. It does not necessarily return the database to its prior state, as other clients may have been making changes in parallel. A rollback only cancels the proposed changes made by this client within the current transaction. Both commit and rollback will end the current transaction, putting SQLite back into autocommit mode. Save points. In addition to ACID compliant transactions, SQLite also supports save points. Save points allow you to mark specific points in the transaction. You can then accept and roll back to individual save points without having to commit or roll back an entire transaction. Unlike transactions, you can have more than one save point active at the same time. Save points are sometimes called nested transactions. Save points are generally used in conjunction with large multi-step transactions where some of the steps are or sub-procedures require rollback ability. Save points allow transaction to proceed and if required rollback one step at a time. They also allow an application to explore different avenues, attempting one procedure and if that doesn't work, trying another, without having to roll back the entire transaction to start over. In a sense, save points can be thought of as undo markers in SQL command stream. You can create a save point with the save point command. Since multiple save points can be defined, you must provide a name to identify the save point. Save points act as a stack. Whenever you create a new one, it is put at the top of the stack. Save point identifiers do not need to be unique. If the same save point identifier is used more than once, the one nearest to the top of the stack is used. To release the save point and accept all of the proposed changes made since the save point was set, use the release command. The release command does not commit any changes to disk, rather it flattens all of the changes in the save point stack into the layer below the named save point. The save point is then removed. Any save points contained by the named save point are automatically released. To cancel a set of commands and undo everything back to where a save point was set, use the rollback to command. Unlike a transaction rollback, a save point rollback to does not close out and eliminate a save point. Rollback to rolls back and cancels any changes issued since the save point was established, but leaves the transaction state exactly as it was after the save point command was issued. Consider the following series of SQL statements. The indentation is used to show the save point stack. Create table T, begin insert into T values 1, save point AAA, insert into T values 2, save point BBB, insert into T values 3, save. At this point, if the command rollback to BBB is issued, the state of the database would be as if the following commands were entered. Create table TI, begin insert into TI values 1, save point AAA, insert into TI values 2, save point BBB. Again, notice that rolling back to save point BBB still leaves the save point in place. Any new commands will be associated with save point BBB. For example, create table TI, begin insert into TI values 1, save point AAA, insert into TI values 2, save point BBB, delete from T where I is equal to 1. Continuing, if the command release AAA was issued, we would get the equivalent of create table TI, begin insert into TI values 1, insert into TI values 2, delete from T where I is equal to 1. In this case, the proposed changes from both the AAA and enclosed BBB save points were released and merged outward. The transaction is still open, however, and a commit would still be required to make the proposed changes permanent. Even if you have open save points, you can still issue transaction commands. If the enclosing transaction is committed, all outstanding save points will automatically be released and then committed. If the transaction is rollbacked, all the save points are rolled back. If the save point command is issued when SQLite is in autocommit mode, that is outside of a transaction, then a standard autocommit begin deferred transaction will be started. However, unlike with most commands, the autocommit transactions will not automatically commit after the save point command returns, leaving the system inside an open transaction. The automatic transaction will remain active until the original save point is released, or the outer transaction is either explicitly committed or rolled back. This is the only situation when a save point release will have a direct effect on the enclosing transaction. As with other save points, if an autocommit save point is rolled back, the transaction will remain open and the original save point will be open but empty. System catalogs. Many relational database systems, including SQLite, keep system state data in a series of data structures known as system catalogs. All of the SQLite system catalogs start with the prefix SQLite underscore. Although many of these catalogs contain internal data, they can be queried using select, just as if they were standard tables. Most system catalogs are read-only. If you encounter an unknown database and you're not sure what's in it, examining the system catalogs is a good place to start. All non-temporary SQLite databases have an SQLite master catalog. This is the master record of the all database objects. If any of the tables has a populated auto-increment column, the database will also have a SQLite sequence catalog. This catalog is used to keep track of the next valid sequence value. The more information on auto-increment, For more information on auto-increment, see primary keys on page 40. If the SQL command analyze has been used, it will also generate one or more SQLite underscore stat hash tables, such as SQLite stat1 and SQLite stat2. These tables hold various statistics about the values and distributions in various indexes and are used to help the query optimizer pick the more efficient query solution. For more information, see Analyze in Appendix C. The most important of these system catalogs is the SQLite master table. This catalog contains information on all the objects within a database, including the SQL used to define them. The SQLite master table has 5 columns: type text, name text, table name text, root page integer, and SQL text. The type column can be table, including virtual tables, index, view, or trigger. The name column gives the name of the object itself, while the TBL name column gives the name of the table or view the object is associated with. For tables and views, the table name is just a copy of the name column. The final SQL column holds a full copy of the original SQL command used to define the object, such as a create table or create trigger command. Temporary databases do not have an SQLite master system catalog, rather, they have SQLite temp master table instead. This is a long chapter packed with huge amount of information. Even if you are familiar with a number of traditional programming languages, the declarative nature of SQL often takes time to wrap your head around. One of the best ways to learn SQL is simply experiment. SQLite makes it easy to open up a test database, create some tables, and try things out. If you are having problems understanding the details of a command, be sure to look it up in Appendix C in addition to more detailed descriptions. Appendix C contains detailed syntax diagrams. If you wish to make a deeper study into SQL, there are literally hundreds of books to choose from. O'Reilly alone publishes a dozen or so titles just on the SQL language. While there are some differences between the SQL supported by SQLite and other major database systems, SQLite follows the standard fairly closely. Most of the time, SQLite deviates from the standard. It does so in an attempt to support common notations and usage in other popular database products. If you're working on wrapping your head around some of the higher level concepts or basic query structures, a tutorial or book written for just about any database product is likely to help. These might be a small bit of tweaking. There might be a small bit of tweaking to get the queries to run under SQLite, but the changes are usually minimal. Popular O'Reilly books covering the SQL language include Learning SQL, SQL in a Nutshell, and the SQL Cookbook. More advanced discussions can be found in The Art of SQL, popular reference book that also include SQL for Smarties and Introduction to SQL. There are two large but very these are two are very large but very complete. There is also SQL Guide to SQLite, which takes a much deeper look at at the SQL dialect specifically used by SQLite. There are also thousands of websites, online tutorials, communities, and forums, including the SQLite mailing lists, where you can get insightful answers to intelligent questions. Before trying too much, be sure to read the next chapter. The next chapter is devoted to the select command. In addition to covering the syntax of the command, it dives a bit deeper into what is going on behind the scenes. That foundation knowledge should make it easier to break down and understand complex queries. It should also make it easier to write them down. That's all for today.